Hello there, this is Truth Socrates. Welcome to my video series on multivariable calculus. So this is video number 25, and we are going to continue with our study of space curves and parametrizations. So last time we learned how to construct a parametrization R of t for a space curve C or a plane curve. Okay, so it could be either in 2 dimensions or 3 dimensions more generally. So today we're going to look at a derivative for these space curves, and we will see how to interpret it, because in the next section we're going to learn how to create an integral over a space curve. So I will see you at page 206. All right, so here we are, the derivative vector of a parametric curve. It's only 6 pages long. Woohoo, a nice short section for a change. So here's our setup. We have a vector function in either 2 or 3 dimensions. We have a domain, an interval I. And what we're going to do is, well, because we have these 3 components and they're all functions of one variable, we can go back to basic calculus and we can ask, well, are you continuous? And even better, are you differentiable? Okay. So if we look at all 2 or 3 components and we recognize them to be differentiable functions, then wonderful. We can define the derivative r prime of t of our r of t as simply the vector function, another vector function, made of the derivatives of the 3 components. Okay, so you just assemble x prime, y prime, and z prime into another vector function. Okay, so that should sound familiar. We start with a function f of x in calculus, and then we create another function f prime of x from f of x. Okay, so we create another function, right? So speaking of basic calculus, okay, let's remember how we define a derivative as a limit. Okay, so thinking about the x component, we have x prime of t is x of t plus h minus x of t all over h, where h is a number which is going to 0. We're taking a limit. Okay, so we're going to write the same thing for y and for z, y prime and z prime. Okay, so we have 3 limits here, okay, and 3 what we call difference quotients, if you remember. Okay, all right, well, we have a common limit here, so why write it 3 times? Let's take it outside. Take it outside. All right, and we have a common denominator here, 1 over h. Take it outside also. Okay, so we just have the differences in the 3 numerators. Big deal. Okay, well, what we can do next is we can create 2 vectors out of this 1 vector. We'll put the parts that have the t plus h in them into 1 vector, and the parts that are left over, the other 3 parts, into a 2nd vector. Okay, now that's a good idea, because now those 3 have the same arguments, t plus h. So this first vector is simply r at t plus h. Okay, and this is of course our r of t. All right, so we get an alternative formula. R prime of t is a limit as h goes to 0 of 1 over h times the difference r of t plus h minus r of t. Okay, so basically what this means is you start at r of t, and then you take a small increment of time. Okay, so remember that t, we can think of it as time. It doesn't have to be time, but that's a convenient way of thinking about t. Okay, so take a split second after t, represented by h. Now where are you? Okay, so remember that r represents position. Okay, you were here a moment ago, and then you changed position to this. Okay, so this difference actually represents the displacement, the change in your position. Okay, so yes, we can call this expression a difference quotient, just as we do in single variable calculus. Okay, so this is what I was telling you about position and displacement, okay? But there is that other portion, which is the 1 over h, okay? Well, h is supposed to be going to 0, all right? So after, when it's sufficiently close to 0, of course, it's smaller than 1 in absolute value. So when you divide by a number smaller than 1, you're actually making it longer, okay? So in this case, we are dividing a vector expression by a number smaller than 1. So we get a longer vector, okay? So let's go over this example just to see exactly what it is I'm talking about. So we have an ellipse, woohoo, okay? So I have this portion of the ellipse, and it's 4 cosine t, 3 sine t. So we have 4, 0 over here and 0, 3 over here, okay? So I plotted these two vectors, and maybe we can zoom in a little bit. Ooh, okay, maybe that's a little too big. So let me just move this over. Can I move you? All right. Let me just bring it back to where it was before. Okay, there we go. So here we are at r of t, and then we're going counterclockwise, okay? So r of t plus h is going to be over here, okay? So there's the difference, r of t plus h minus r of t, right? So when we divide by h, that difference becomes longer, okay? So let's make h a little bit smaller. Yeah, that's what's happening over here. Check it out, okay? So now we increase t by a smaller amount of time, so we didn't move as far as we did previously, okay? So that's a very small change in position, and I didn't even label it because otherwise it would just clobber that vector. So if we divide by h now, it gets longer again. But look at that. This vector and this vector, don't they look almost the same in length, right? So even though the difference is shorter in the second example, we're also dividing by a smaller h, okay? So that compensates for this smaller vector, and what we get is pretty close to where we were before, all right? So of course, as you take the limit, ooh, okay, there it is, okay? All right, well, what's the formula? All right, the ellipse is 4 cosine, 3 sine. We know how to derive trigonometric functions. Derivative of cosine, negative sine, so minus 4 sine. Derivative of sine, cosine, so 3 cosine of t. All right, so that is the idea. We have a parametric curve. It can be on the plane. It could be in space. And we take the derivative of every component. Okay, it represents what looks like, okay, remember back in calculus, the derivative is like a tangent line, or more specifically, the slope of a tangent line, okay? The advantage here is that what we get is a vector, and doesn't that look like what you would call a tangent vector at that point, okay? So we draw it with the tail at the point, or we can say rooted at the point, because yeah, it doesn't have the same satisfying feeling as if you would draw it from the origin. It looks much nicer when you root it at the endpoint of the position. Okay, so let's go to our workroom and let's look at some of the examples that we saw from our last video. Let's find their derivatives. All right, so we're going to recycle some of our examples from last time. But for our first example, I'm going to make it a little bit more specific, okay? So we found the parametric equation for the line passing through A and B. But let's make it more specific, okay? Find the vector equation for the line from point A to point B, okay? Same numbers from last time, okay? So first we got the direction vector, which is 1 plus 5 minus 2 minus 7, 6 minus 3. okay? So there is our direction vector. But if you compare this to our last video, we said, well, you know, we can ignore a factor of 3, okay? However, because I want to start at A and finish at B, let's keep that direction vector just the way it is, okay? So the R of t that we get is the starting point, minus 573, turned into a vector, plus t times the direction vector, okay? Our goal is to find the derivative, okay? So obviously the first thing we want to do is, well, let's create just one vector, okay? So of course, when we went to GeoGebra, we use the curve command and we have to put everything into a single vector. Okay, so we have minus 5 plus 6t for x. We have 7 minus 9t for y. And 3 plus, another 3t for z. So that is our final vector function. Look for the derivative. Okay, well, that's pretty easy, okay? Derivative of the first term is 6. For the second term, we have negative 9. Whoops. Minus 9 right there. And for the third term, we have 3. Where did those numbers come from? Oh, of course. Those are that is just our direction vector. Okay, so that makes perfect sense. Okay, if you're going from point A to point B and you're moving along a straight line, well, that just means that the velocity is pointing in the direction of motion. Okay, so it's simply the direction vector of our line segment. Okay, all right, so let's move on to our next example. Okay, so this was a little bit more interesting. We have a circle, but we only want the right half, and we found a parametrization for it. So the center is at 5, negative 2. The radius of the circle is 4. So our parametric equation is starting at the center, 5 minus 2. You move around, think of the unit circle, so it's parametrized by cosine and sine, but we want the radius to be 4. Okay, so we add 4 of that vector. We only want the right half, so we can choose as our domain either minus pi over 2 to pi over 2 or 3 pi over 2 to 5 pi over 2. Okay, so what is the derivative here? Well, you're pretty good at putting vectors together, right? So I'm going to skip that step. We can see it right before our eyes. Our x component is x plus 4 cosine. So the derivative is just negative 4 sine of t. And our y component, there is no z, is minus 2 plus 4 sine t. So that's just 4 cosine of t. Okay, so that looks like our ellipse example from a while back. Okay, but of course, the coefficients are the same in this case in absolute value. Okay, because we have a circle over here. All right, so let's go to GeoGebra and let's plot this circle and let's draw a couple of tangent vectors. All right, so we remember curve, and we have 5 plus 4 cosine of t, and negative 2 plus 4 sine of t. T is going from, how about minus pi over 2 to positive, hate it when it does that, to positive pi over 2. Aha! So there it is. Scoot over here. There is our half circle. Okay. We have our derivative, okay, but we're not going to graph the derivative function, okay. We're going to plot values that we obtain from that function when we plug in a certain t, okay. So let's start with plotting a point first on that half circle, all right? So how about just pi over 6, okay? So I can literally, I think, just copy this. Oops, I'm sorry. I need to get in there. Copy this, and then, haha, I will just replace t with pi over 6. Put a comma in. Haha. There we go. And that other t with pi over 6. Oops, 6. There we go. Okay. Oh, it's right over there. Okay. So check it out. Yeah. If you're at the center, then that angle is literally pi over 6. Okay. So we're on the x-axis. Nothing wrong with that because sine pi over 6 is 1/2. So we have -2 plus 2, and we get a 0. Okay. However, the derivative is -4 sine t for cosine of t. Okay. So let's press enter. That's a point. Okay. We have a vector which is -4 sine t for cosine t. So -4 sine pi over 6 and +4 cosine pi over 6. Oops, I always do that. Okay, there you go. You need parentheses. Stupid parentheses. Okay, so there's that vector. Okay, but it's at the origin. Okay, and I said, that's not really very satisfying. Okay, it would look nicer if it were rooted at point A. Okay, so one thing you can do is you can say vector from point A to point A plus U. Ooh, okay, so there it is. Okay, so now that it's there, we can hide that vector, and you will still see that tangent vector. Okay, so yeah, if you look this way, it does look like it's just kissing the circle at that point. Okay, so of course you can draw a similar tangent vector at any other point that you want. Okay, you can choose -pi over 3 down here, or -pi over 6 over here, for example. Okay, so let's go back to our workroom then, and we'll take a look at another example. All right, so this is a little bit more fun. It's in 3 dimensions. We have an elliptic helix, okay, where t can be any real number. Okay, what is the derivative? So again, we have a little bit of trig. We have -3 sine of t, and then 2t becomes just t. I'm sorry, just 2. Okay, and 5 sine t becomes 5 cosine of t. Okay, there we go. So let's go to GeoGebra. We will graph the helix, and we'll graph a couple of tangent vectors. Okay, 3 dimensions. So we have curve. And 3 cosine of t, 2t, and 5 sine of t. So let's go from, how about -2 pi to +2 pi? So just -6, +6. Okay. All right. So we have this elliptic helix. Zoom out. So you can say, ooh, there it is, forming right before our very eyes. All right, we have that beautiful elliptic helix. It's just a coil, okay, or a spiral, okay? But of course, it from that view, it looks like a helix. I'm sorry, an ellipse, okay? All right, so again, let's plot a point, okay? So yeah, let's just type it out manually. So how about 3 cosine at pi over 3? And then we have 2 times pi over 3. And then we have 5 sine pi over 3. Okay, so there we go. There is our point. Okay, it is clearly on the elliptic helix, and we can now zoom out. Okay, because we're really just interested in that part of the helix. Okay, so what can we do now? We can draw the vector at that point without plotting an intermediate vector. Okay, all we have to do is just type in the derivative vector directly. Okay, so we have minus 3 sine of pi over 3. And then we have 2. Ooh, check it out. And we have 5 cosine of pi over 3. Aha! There it is. Okay, so yes, notice that it does look like back in calculus when we saw tangent lines. Okay, but of course it only goes in one direction. Okay, you don't have literally a tangent line. However, if you do want a tangent line, you can make it. Okay, because we know a point on the line and we know a direction for the line. Okay, so you can create, just like we did in the last video, a parametrization for the tangent line to that helix. Okay, but of course, now that we have that tangent vector rooted at that point, we get practically the same effect. Okay, so that's it. As I said, it's only 6 pages long. That's the basic idea. You have a vector valued function. Can you take the derivative of all 3 components? Wonderful. Go ahead. Now you can make r prime of t. What is the meaning of r prime of t? At any point on the curve, if you draw the value of that r prime vector, then you get what is called, what looks like a tangent vector to our curve. Okay, so I hope you enjoyed that very short video, and I'll see you next time when we can actually now set up and compute a contour integral over these curves. The derivative, of course, is going to be important. That's why we're doing it. Okay, so until next time, I hope you enjoy the rest of the day. Bye.